Hello everybody, this video is going to be about calculating percent composition and something called empirical formulas. Percent composition is when we are trying to figure out how much of a molecule's mass is coming from each of the elements. So we're trying to see how much each element is contributing to the mass. And we typically will do this as a percent. Now, if you remember from math class, a percent is typically described as a part of something divided by the whole. So it could be how many pizza slices you ate over how many came in the box, right? Something like that. So for percent composition of a molecule, it will be the element's mass from the periodic table divided by the mass of the entire molecule times 100. That will give us the percent from that particular element. So we'll find the molar mass of the entire molecule of the whole. We'll divide it, each element's mass, by that molar mass that we just found for the whole molecule. And then we'll put it into a percentage. Now, if you do everything right and you add it all up, it should add back to 100%. If you have 90% of one element and 10 of another, it should add back to 100. However, sometimes with our rounding, because we're not going to go out to infinite number of decimal places, sometimes we will end up with it not adding quite back to 100. Totally fine, not an issue. If it's an issue of rounding, I will be able to figure that out. Okay, don't worry. All right, if there's a mistake, that's different than a rounding difference. Okay, so let's do an example. Calculate the percent composition of magnesium carbonate. Wow, what do you know? I didn't give you the formula, did I? I expect that you know what the formula for magnesium carbonate is. And you should have memorized your polyatomic ions to know what carbonate is, right? So you're going to see that we can start adding in some of those early first semester topics, assuming that you know how to do them by now. So we have magnesium is a +2, carbonate is a -2. Right? Carbonate is CO3 2-, so we get a 1-to-1 ratio. We have one magnesium and one carbonate. So let's find our entire molar mass. Magnesium plus a carbon plus 3 oxygens gives us a total mass of 84.32 grams per mole. I'm going to start with magnesium. Magnesium weighs 24.31. I divide it by the total molar mass of the molecule. I find out that it's 28.83% magnesium. Now it's carbon, 12.01 divided by the total mass times 100 tells me that this molecule is 14.24% carbon. Last, the oxygen. Now be careful here. You're not going to put 16. You don't have 1. You have how many? You have 3. So you need to put the total mass of your oxygen over the mass of the molecule. Be very careful about that. I would make a big giant note somewhere in your notebook, bright red, fluorescent highlighter yellow, something. Big stars, arrows. That's one of the most common mistakes I see. At the end, suggest that you check to see that it adds back to 100 or almost based on the rounding. Everybody always says, wait a second, if you found the first 2, couldn't you just subtract from 100 and find out what the last one was? And yes, you can. However, if you made a mistake in one of these parts and then you subtract, you're going to get the last part wrong too. So I highly suggest you do each one individually, because that way, if we're giving partial credit for each element and you got 2 of your 3 elements, right, you can get partial credit. The subtraction is the little risky because your final answer is now going to depend on whether or not you got the first ones correct. Maybe you did, and that's fine. I'd be a little bit careful. Moving on, we're going to find out how to do empirical formulas. Empirical formulas is the simplest, most reduced version of a formula, the smallest whole number ratios you can get. This may or may not be the real formula. Remember that we reduce ionic formulas down, but we don't reduce molecular ones, right? When they're covalent, we don't reduce them. So an empirical formula may not be the correct final molecular formula. You just have to check and see. The empirical formulas are important, even though they may not always be correct, because it gives us the ratios that we would get from our equipment in the lab. We have types of equipment that can tell us how much of each element we have in a percentage form. That will help us find the empirical formula, and then from that we can find the molecular formula. So it's not that empirical formulas are very helpful for anything, specific. It's that we have to know how to use them because of how our equipment works. So a couple examples. C6H6 is the molecular formula. That's the real formula. But the empirical formula, there we go. The empirical formula reduces those 6's down. We can see here it's a 1-to-1 ratio, right? We don't typically tell people it's a 6-to-6 ratio, right? That sounds a little funny. Most people reduce them down, say it's a 1-to-1. So you can see that's what the empirical does. Ionic formulas are always empirical. We always reduce them down. You're not going to say sodium 3, chlorine 3, right? You would reduce them. Covalent ones, sometimes empirical, sometimes not. Water is already as low as it can get, right? So that is already an empirical formula. C6H12O6? Nope, that's not reduced all the way. This is the real formula. This is what the molecule actually looks like. But the empirical formula would be CH2O. C12H22O11. Oh, that's already reduced. It's not a lot of small numbers. Those are pretty big numbers, but I can't get them any smaller, right? We got this odd number over here. It's not playing nice with everything else, right? So this is the empirical formula. So to find your empirical formula, you're actually going to remember a silly little poem, okay? So to determine this formula, you are almost always given a percent composition. Almost always, that's what they're going to give you. To make your life easy, you're just going to assume that you have a 100-gram sample, that you're putting 100 grams into the machine. If you do that, then if it's 40%, well, 40% of 100 is 40 grams. 30% of 100 grams, right, is 30 grams. It just makes your life easier. If you put a, 62-gram sample in, then you're going to have to do a lot more work. Just pretend it's 100 grams, and you're going to use the poem. The poem's really silly. It's short, but it's the thing that basically every chem teacher I've ever known has used. So it's a great way to remember how to do this. We say percent to mass, mass to moles, divide by small, multiply till whole. So we're going to take our percent composition, assume we have a 100 gram sample, and convert those percentages to gram masses. Then we're going to convert into moles because, as always, the mole is the key to everything. Dividing by small is going to help us find the smallest ratios possible. And then multiply till whole will make sure we take those ratios and make sure they're in whole number increments. We are never going to have part of an atom. So that's the idea behind this little poem. So let's give it a try. So we have 49.32% carbon, 43.84% oxygen, 6.85% hydrogen, and we want to know what that empirical formula is. So step 1, percent to mass. I'm pretending I have a 100 gram sample, so I just swap my unit, make it easy. If for some reason they told you that you had a different size sample, then I suppose, maybe you have to do the actual calculation, but that's rare. Now, mass to moles. You have 3 different elements in grams, 3 different conversions using molar masses. 3 molar masses to use, 3 answers you're going to get. One of the reasons that we have been on you so much about how fast you can do these conversions is because you should be seeing that these problems start stacking and getting longer and longer. Now, instead of doing 1 molar conversion, you're doing 3 molar conversions in step 1 of a long problem, right? So let's do those conversions. Mass to moles. Carbon, hydrogen, oxygen. You should notice something immediately that would be a common mistake. We have hydrogen and oxygen here. They tend to be diatomic gases. But I don't have diatomic gases here, do I? I have elements that are bound inside a molecule. It's not a diatomic gas floating around. So look at the masses that I'm using. Hydrogen is 1.01 because I'm not using diatomic hydrogen gas. I'm just using the element, the atom hydrogen. Same with oxygen. It's not 32, it's 16. We're just using the regular old singleton of oxygen here. Yes, that's tricky. Yes, it's something you have to remember. That's what makes chemistry hard. We have things like that, right? So make a note to yourself, draw attention to that so you don't make that mistake somewhere else. So we've done the first 2 lines of the poem. We did percent to mass, mass to mole. Now it's time to divide by small. You're going to look at the moles that you have, and you're going to divide them all by the smallest number you got. So for carbon, the smallest number of moles was oxygen. So I'm going to take carbon and divide it by that number, and I get 1.5. I'm going to take my moles of hydrogen, divide it by the smallest number of moles that we got, and this is what I get. I take the moles of oxygen, divide it by the smallest. Oh, look at that. Oxygen was the smallest. I'm dividing by the smallest. That's silly, but that gets me a 1 over here. Okay, so I've shrunk all these ratios down as far as I can, but you should notice these aren't whole numbers, are they? It was too far. We went too far. Yes, we were able to get down to a single 1, but that made these decimals, and we need them to be whole numbers. So now what we have to do is we have to multiply till whole. We have to take those ratio numbers we found, get them to be whole numbers. If I do something to 1 element, I have to do it to all of them. If I multiply something by a 4, they all have to get multiplied by 4. If I multiply by a 2, they all have to get multiplied by 2. So whatever you do to one, you have to do to all of them. The other thing that's hard is that the decimals are not always perfect. Realize that this is all coming from lab data, okay? Lab data is not perfect. So our percentages and things are going to end up not quite perfect. So carbon 1.5, wow, that turned out really good, huh? But look at poor hydrogen. 2.47, you need to be able to have some judgment, and you need to say, you know what? That's close enough to 2.5. Let's just round to 2.5 to make our life easier. Oxygen's already good to go. So now I need to look at these numbers, and I have to figure out what is the smallest number I can multiply them by to get every single number here to be a whole number. This time I can multiply everything by 2. That means I'm going to have 3 to 5 to 2 ratio. And those become my coefficients for my empirical formula, which is the smallest ratios I can have, okay, that are still whole numbers. Usually these decimals will turn out to be like 0.25, 0.5, 0.75, but you could have like 0.33, right, 0.66. They could get even trickier. I suppose you could have, an eighth thrown in or something, right? Or a fifth or a seventh or, whatever random numbers. But it's not as common as the quarter and the half and the 3/4. Those are pretty common fractions that you end up with. So now we have our empirical formula, but we need to be able to get from an empirical formula to the true actual molecular formula, the real formula for that compound. So you have to find the molar mass of the empirical formula, and then you're going to be given the molecular formula mass, and you're going to divide them. Then you're going to multiply by the same multiplier. The sad part is there's no rhyme for this portion, okay? The rhyme is only for the first part. So let's finish this problem up. You're told that the molecular mass is 146. So our empirical formula mass was 73.08. This is the formula we got earlier. Now I take the mass of the full molecule. I'm going to divide it. I'm going to get an answer. This tells me that my molecular formula is twice whatever my empirical was. So I take my empirical formula and I'm going to double it because the mass was double what the empirical mass was. If it was triple, then down here I'd be multiplying by 3. If it was 5 times bigger, I would multiply down here by 5. So we're trying to see how much bigger is our molecular formula. If you get a 1 on step 2, if you have the same molecular and empirical mass, then you're done. It means that there's no multiplier, right? It means that the empirical is the same as the molecular formula. I always feel like these problems sound way more complicated until you've done about 3 of them. After about 3 problems, they get so repetitive. You're going to just be on autopilot going through your little rhyme and then you'll be all done, right? So give it a few problems, that if you need help, come ask. Okay? All right, everybody. I hope that was helpful. Bye.